Okay, so let us continue our solutions with exercise 61. Here we have to prove that no group can have exactly two elements of order 2. Let G be a group and let A and B be two distinct elements of order 2 in G. We will now show that there is another one. Besides A and B, there will be another element of order 2 in G. Assume first that A and B commute. Then AB square is A square times B square because A and B commute, and because A and B both are of order 2, so both these powers are equal to the identity. So this becomes the identity. If we suppose this equation itself does not tell us that the order of AB is 2. It only says that the order of AB is either 1 or 2. Now, if we suppose that the order of AB is 1, that is, if we suppose AB is the identity element, then A is equal to B inverse, but because B square is identity and that is coming from here, B square, B has order 2, so B square is identity, so B inverse is equal to B. Contradicting the distinctness of A and B. So AB is different from the identity. Thus, AB has order 2. Note that by the cancellation laws in G, AB is different from both A and B, because if AB is equal to A, then B has to be the identity, and in that case B will have order 1, not 2. Similarly, AB cannot be equal to B. So our assumption that A and B commute has led to the uh, conclusion that there is another element besides A and B which is also of order 2 in G. So in this way, if there are at least two elements, then there are at least three elements of order 2 in G when those two elements commute. Next, assume that A and B do not commute. Now we will show that ABA is an element in G which is of order 2 and which is different from both A and B. Note that ABA whole square is ABA times ABA. So this first of all gives us ABA square BA. Now since A has order 2, so A square is identity. So E vanishes and we have AB square A. B also has order 2, so B square is also identity and we have A square which finally gives us identity. Okay. If we suppose ABA equal to identity, then AABA times A equal to A square BA square, that is equal to B. But at the same time, that is also equal to, wait, I want to conclude from this that something goes wrong. But what goes wrong? If I multiply on both sides by A, then here I am getting B. Okay, so I should have started not from here but from here. E equal to A square because A has order 2 and A square can be written as AEA, and in place of this E we now substitute ABA, and this gives us A square B A square or EBE or B, which, but then B is identity, which implies order of B is 1, a contradiction, which contradicts that the order of B is actually 2. So we must have ABA not equal to identity, and just like before, this implies that ABA has order 2, which comes from this one and this equation. And hence the order of ABA is 2. But how is ABA different from A and B? Instead of showing that by contradiction, can we do it directly? Note that since A and B now do not commute, so AB is not equal to BA, which implies if we multiply on both sides by A, post multiply on both sides of this inequality by A, then the resulting group elements will also not be equal by the cancellation law. So ABA is not equal to BA square, which implies ABA is not equal to BE, and hence ABA is not equal to B. If you find these implications somewhat confusing because they have inequality, you can of course suppose that ABA is equal to B, and then you can proceed and ultimately you will have AB equal to BA, which will contradict our assumption that A and B do not commute. Note that that way of showing things is equivalent to this way of showing, because there also you will have a sequence of implications. Here also you have a sequence of implications, and if you look carefully, those two those two sequences are equivalent because they are in each sequence. An implication has a corresponding contrapositive that is there in the other sequence, because in that sequence you will start by considering the negation of this, right? ABA equal to B, that will imply this, negation of this, which will imply negation of this. So the fact that we have written these things already implies that they are coming from that sequence, and conversely also. Okay, so we have this. Similarly, one can show that ABA is not equal to A. In order to show that, we pre-multiply both sides by A. So on this side we will have ABA, on this side we will have A square B, but then again we are getting B on this side. So we have to get rid of B. So we can, if we pre-multiply, or I think this way of showing is becoming confusing for me also. You show it the usual way. You assume that ABA is equal to A, then that will imply what? Oh, that is something different, okay. So it will not proceed in this way. If you assume ABA is equal to A, then you can cancel one A from both sides. That will give you what? Say if you cancel this A on the left hand side, then you end up with BA equal to E, which will imply that A and B are inverses of each other, and you will end up with a conclusion like this, that A is equal to B, which is not true. It again contradicts the distinctness of A and B. So that's how you can show that these two things are not equal. So that's it. In any case, whether A and B commute or they do not commute, we have shown that there is a third element also in the group which is of order 2. So we can never have exactly two elements of order 2 in any group. So this completes the solution. Let us now see the 62nd one. Given the fact that U49 is cyclic and has 42 elements, deduce the number of generators. Number of generators that U49 has. Without, of course, actually finding any of the generators. Okay, in this case, the solution goes like this. By the third corollary, by corollary three to theorem 4.2, the number of generators of U49 is the Euler phi function value of the order of this group. For you visit this corollary, you see its statement, you will understand why this number is this. Phi of the order of the group. Now 42 is what? 21 times 2. So that means this. So phi of 42 will be 42 times, this is the prime factorization, 1 minus 1 over 2 times 1 minus 1 over 3 times 1 minus 1 over 7. This is what we should really not write like this, okay, striking these things out and then writing, but just for the sake of showing what's going on, we are doing this. So this is 12. So there are 12 generators of U49, and we haven't found any generator. Actually, we just have found the number of generators. (63). Let A and B be elements of a group if order of A is 10 and order of B is 21, show that the intersection of the cyclic subgroups generated by A and B is the trivial group consisting of the identity element only. Let C be any element in this intersection. Then C belongs to both the cyclic groups, and from elementary properties of cyclic groups, the order of C should divide the order of this subgroup, and also the order of C should divide the order of this subgroup, which are nothing but the order of this first one is nothing but the order of A itself, and the order of the second one is the order of B. Then C should divide the order of this, which is equal to the order of A, that is 10, and like that C should also divide this, which is 21. Hence, not C but order of C. Because C is a group element. Hence, order of C divides 21 and it divides 10. So by elementary properties of divisibility, it divides 21 minus 2 times 10, which is nothing but 1. Now, since order of C is by definition a positive integer, whatever it is, it's a positive integer. Since this is the positive integer, we have order of C equal to 1, but there is only one element in any group whose order is 1, namely the identity element. Thus, C is the identity element. So, This intersection has only one element, and that is the identity element, which proves this. If you want, you can write this final conclusion in the solution. The next one is also similar, but it's more general than this. (64). Let A and B belong to a group. If the order of A and the order of B, now they are not, no value is given, but it's given that they are relatively prime. Then the conclusion is like the previous one. Show that the intersection of these two cyclic subgroups is the trivial group. So this 21 minus 2 times 10, which is giving us 1, it looks like an ad hoc calculation which has worked in this case, but this, of course, you know, is a general property of integers that are relatively prime. For such integers, there is a linear combination of those integers where the coefficients are also integers, that is equal to 1. So you can probably already see what I am going to write here. Since instead of writing in words, we can more compactly write the same thing in this way. Being relatively prime means their greatest common divisor is 1. So there exists integers, say alpha and beta, such that alpha times order of A plus beta times order of B equal to 1. Let C be any, like before, C is any element in this intersection. Then the order of C divides. We can write directly now, because since we have already seen what goes on here. Which imply that this order divides this linear combination, which is 1, and then the rest is a repetition of the previous solution. Also, I am not writing that. Okay. You just simply write all these things starting from here and ending here, and that will give you the solution. 65. This time again another one such exercise, but here the orders are not relatively prime. Let A and B belong to a group if order of A is equal to 24 and order of B is equal to 10. What are the possibilities for the order of this intersection? What are the possibilities for the order of this intersection? Okay. So now we cannot okay, note one thing, that this intersection, not its order but the group, the intersection is a subgroup of this cyclic group. At the same time, it's a subgroup of this cyclic group also. So from the properties of cyclic groups, this order should divide this order, and this order should also divide the order of this one. Yeah, from there we can then proceed. Since this is a subgroup of both this and this, we have this order dividing this order, which is 24, and like that, this order also divides the order of the cyclic subgroup generated by B, that is 10. So this is a positive integer, right? It is the order of some group. This is a positive common divisor of 24 and 10. So it should divide the greatest common divisor of 24 and 10 by elementary properties, in fact by the definition of GCD. Thus, we have this dividing the GCD of 24 and 10, which is 2. Hence, there are only two factors of 2, two positive factors of 2, 1 and 2, because 2 is the prime. Hence, this intersection has order either 1 or 2. So these are the possible orders of this intersection. 66. Prove that the group U2 to the power n, where n is at least 3, is not cyclic. Okay. So for any such n where n is at least 3, that means for n equal to 3 or 4 or some higher values, this group is never cyclic. Okay, now what can we possibly do here? We will try to show that being a cyclic group leads to some sort of contradiction. Suppose this is cyclic with some generator A. Cyclic means there will be some generator in the group which will generate the whole group. Then what is the order of A? The order of A then will be the order of the group, which is the Euler phi function value of 2 to the power n. Since the only prime factor of the number 2 to the power n is 2, so just like before, this is 1 minus 1 over 2, which is 1 over 2 itself, so we get 2 to the power n minus 1. Okay. Now we will observe that this group has two distinct elements of order 2. We are not saying it has exactly two distinct elements. We have already seen that that is not possible. At least two distinct elements of order 2 are there. Note that 2 to the power n minus 1 belongs to this. How do we know that this integer belongs to this? That is because this and this are relatively prime. Note that this belongs to this such that what is its square modulo 2 to the power n. Expanding using binomial theorem, it is 2 to the power 2n minus 2 to the power n plus 1, because 2 times 2 to the power n plus 1 mod 2 to the power n. Since we have 2 to the power n here in these terms, so they contribute 0 to this, when we calculate the mod. So we end up with 1. Okay, and 1 we already know is the identity element in this group. So the square of this element, that's how we will calculate the square in this group, right? Using modulo 2 to the power n. So square of this element is identity. So the order of the element 2 to the power n minus 1 in this group will be 2, provided the element itself is not identity. Since 2 to the power n minus 1 mod 2 to the power n is not equal to 1. Why? Because if this had to be equal to 1, 2 to the power n mod 2 to the power n had to be equal to 2, but that is 0, and 0 is not equal to 2, so that's why this is not 1. Order of 2 to the power n minus 1 is equal to 2. Like that, also there is another element like this, which is 2 to the power n minus 1 plus 1. This also belongs to u 2 to the power n. It is also relatively prime to 2 to the power n. The reason is that if you how is this relative? This is relatively prime to 2 to the power n because the only prime factor of 2 to the power n is 2, and it does not divide this because this is an odd integer. That's why they are relatively prime, such that we are now going to calculate its square also. Modulo 2 to the power n. Use binomial expansion first, plus 2 to the power n minus 1 plus 1, so this plus 1 mod 2 to the power n. Again, this thing is equal to 1 because n is greater than or equal to 3. Note that because n is greater than or equal to 3, 2n is greater than or equal to 6, and that's why 2n minus 2 is greater than or equal to, no, that's not what I want to conclude from this. What I'm trying to say here is this. This can be written as 2 to the power n times 2 to the power n minus 2, and because n is greater than or equal to 3, this is an integer. That's what I'm trying to say, and that's why this is divisible by 2 to the power n, and hence its contribution to this number is, or contribution to this remainder is 0. That's why we have 1, and this of course is also divisible by 2 to the power n, it's 2 to the power n itself, and this one is 1. Okay, so in this group, this element also is 1 whose square is the identity. Now, like that previous one, we now have to conclude that, argue that the element itself is not equal to 1, since is not equal to 1. Because for that to happen, for this to be equal to 1, 2 to the power n minus 1 should be divisible by 2 to the power n, which is not true. So that's why this is not equal to 1. So we have this element also of order 2. Okay. Now these are elements in u2 to the power n, and according to our supposition, u2 to the power n is cyclic and has generator A. So that means both these elements will be some sort of powers of A. Let this be a to the power I, and this one be a to the power j. Okay, now we apply the formula for the order of a to the power I in terms of the order of A. We have this thing in the theory of cyclic groups. We know that this order is 2, so let us write that 2 equal to this, which is equal to order of a to the power I, and by the formula that I am talking about, this is nothing but the order of A divided by the greatest common divisor of the order of A and I. Okay, now we know this order, 2 to the power n minus 1, and here we have GCD of I. So what do we get from this equation? This implies GCD of this is equal to this divided by 2, 2 to the power n minus 2. So greatest common divisor of these two things is equal to this. So the greatest common divisor should divide I, because after all it's a common divisor. So 2 to the power n minus 2 divides I. Okay. And at the same time, I is definitely less than or equal to 2 to the power n minus 1. Actually you can take some other value of I also, but I mean there exists one I. So here what I am trying to say is that because all the elements in the cyclic group will be powers of A and the cyclic group is finite, so these powers of A are sufficient to get all the elements in the cyclic group. 2 to the power n minus 1 minus 1. Okay, so I in any case is less than or equal, in fact strictly less than 2 to the power n minus 1, and this divisibility relation implies we have this. So I lies between 2 to the power n minus 2 and 2 to the power n minus 1. But since the GCD is 2 to the power n minus 2, I cannot be 2 to the power n minus 1, because in that case the GCD will be this, not this. So that means I has to be equal to 2 to the power n minus 2. By assuming we get I equal to 2 to the power n minus 2. But what we have done with I, we can also do with J. In spite of having a different element, nothing actually changes because we are considering the order of the element, not the element itself. Similarly, J is also equal to 2 to the power n minus 2. Then what do we get? If I and J are actually equal, then these two elements are actually equal. So that means these two things are equal. Then 2 to the power n minus 1, but their equality should be interpreted in this group. That means these two things must be equal. 2 to the power n minus 1 plus 1 mod 2 to the power n. And these two things being equal means what? It is equivalent to saying that the difference of these two ordinary integers is divisible by 2 to the power n. This divides difference 2 to the power n minus 1 minus 2 to the power n minus 1 minus 1. Okay, now what do we get from this? From these two integers, we can take 2 to the power n minus 1 common out. Then you will have 2 from this term minus 1 from here. And this minus 1 and minus 1 give us minus 2. Okay, so we have 2 to the power n minus 1 minus 2. Okay. And this is not possible. Why is this not possible? See, this integer is less than 2 to the power n. Naturally, because already 2 to the power n minus 1 is less than 2 to the power n, and on top of that we are subtracting 2. So that is making it even lesser than 2 to the power n minus 1. So the only case in which this can possibly be divisible by 2 to the power n is when it is equal to 0. But for that to happen, that can happen if n is equal to 2. But that is not the case because n is greater than or equal to 3. Since is less than 2 to the power n, but at the same time it is greater than or equal to 0, or we can in fact conclude at once that we have hit a place from which there is no escape, since 0 is less than this and this is less than 2 to the power n. We have a contradiction. And the reason for this integer to be positive is that n is greater than or equal to 3. In brackets, we emphasize that fact by writing it. Note that n is greater than or equal to 3. And that is why our first supposition that the group is cyclic is not true. So, our supposition is wrong. That is, u to the power n is not cyclic. Note that here we have actually needed this condition quite essentially. I mean, even in the smallest possible case, if we take n equal to 3, then also this becomes positive. The smaller one, n equal to 2, gives us 0. Okay, so in that case we cannot proceed like this. But luckily, and in fact that's why it's given to us like this. So that's it. This completes the solution. Suppose that G is the group of order 16. and that by direct computation I need ink. And that by direct computation you know that G has at least nine elements. X such that x to the power 8 is equal to identity. Can you conclude that G is not cyclic? Another part, what if G has at least 5 elements? This is the different G, okay, not this G. If G has at least 5 elements, but the order stays the same, order is still 16. X such that this, and then generalize, and this all the parts of this exercise depend on just this fact. We know that in a cyclic group there are at most n solutions. To the equation x to the power n equal to e. So if the group has, if we already know that there are at least 9 different solutions to this equation, then it cannot be cyclic, because had it been cyclic, there would be at most 8 different solutions. The actual number of solutions may be less than 8, but at most 8 different solutions to this equation. So existence of 9 different solutions at least tells us that the group cannot be cyclic. The same conclusion is to be drawn here also, because if we have found at least 5 different elements that satisfy this equation, then by this fact it cannot be cyclic again, and this is the general situation in which it cannot be cyclic. '68. Prove that this group, we already know that it's cyclic, but now it's about the number of generators, that this group has an even number of generators if n is greater than 2. Okay. And this is how we can solve this. Let X be a generator of this. Then X is an element in Zn which has order equal to n. And this implies, we know that not just in Cn or any cyclic group, in any group, the order of an element, if it is finite, is the same as the order of its inverse. And if the element is of infinite order, then its inverse is also of infinite order, which is very easy to prove. You just have to apply the definition of order and you can prove this fact. This implies that the order of X inverse is also equal to n. If n is greater than 2, then X is not equal to X inverse. Why? Because otherwise X is equal to X inverse, which implies X square equal to identity, which implies n divides 2, n, which is the order of X, should divide 2, but then n has to be less than or equal to 2, but here it's given that n is greater than 2. Hence, so we see that any generator gives us another generator which is different. So all the generators of Cn occur in pairs. Hence, all the generators The number of generators in Cn is Zn or Zn, whatever you want to call it. It is a finite group, so there will be finitely many generators, but whatever be the number, it will always be even because the generators occur in pairs. And let us solve another one. If the order of a to the power 5 is 12, where a of course is an element in a group, what are the possibilities for the order of A? If the order of a to the power 4 is 12, first assume that we have this. Now we know the formula for the order of a to the power 5 in terms of the order of a, and we are going to use that. Then 12 is equal to this, which is this order divided by this. Now note that the GCD of this and 5 should, by definition of GCD, be a common divisor of the order of a and 5. That means it should divide 5, and since GCD by definition is positive, so it will either be 1 or 5. Okay, since this divides 5 and this is a positive integer, either this is equal to 1 or it is equal to 5. If the GCD is 1, then this is 1. In that case, order of A is 12, and if the GCD is 5, then the order should be 60, because 60 divided by 5 is 12. So these are the two possibilities. Either the order of A is 12 or it is 60. Next, assume Next, assume that the order of a to the power 4 is 12. Then, just like before, or let us simplify or making it more complicated, that does not matter. We manipulate the equation and write it like this. Since, again, same sort of argument, since GCD of this and 4 divides 4, we have this equal to 1 or 2 or 4. If the GCD is 1, then, oh, there is one more thing. Have we forgotten to see what happens? I mean, do we really have these cases? Are they possible, or are we just simply writing them from this equation? If order of A is actually equal to 12, then since 12 and 5 are relatively prime, so yes, the equation is satisfied. And when order of A is 60, then the GCD of 60 and 5 is, yes, it is equal to 5. So 60 divided by 5, 12. Fine. Okay, now if the GCD is 1, then what do we get? Order of A is equal to 12. But then this is equal to 4, which is not equal to 1, because this is 12 and 4 divides 12, so GCD will be the divisor. And so this case actually does not arise. That's what I wanted to verify there. If, on the other hand, GCD of these two things is 2, then what is order of A? It will be 24. But then again we have problem. This is again going to be 4 and not equal to 2. So these two cases above do not arise if GCD of these two numbers is 4, then the order of A is 48, and in this case, yes, it is, things are, it is satisfied, this equation, because on this side we have 48 and on this side the GCD of 48 and 4 is 4, and 4 times 12 is 48. So yes, this is, in this case, this is the only possibility. And here I could have continued with one more, okay, the 70th one, but let us do it in the next video, because I have not, the next one asks us to find a necessary and sufficient condition for something. I have found a condition, but it's not very satisfactory. So we will see that in the next video. So that will be all in Gallian's group theory exercises in this video. If you want to comment something on this, you can write in the comment section below. So that will be all for tonight in group theory from Gallian. So until the next video, okay, what do we have tomorrow? Tomorrow is what? Tuesday, no? Actually this itself is tomorrow, but I'm just saying tomorrow is Tuesday. That means we have group theory from Herstein's topics in algebra. Okay, so until then, this is me, Lucifer, from a mathematical group. Have a nice night.